Welcome to topic 10.3. In this lesson, we are going to work on identifying what are called limiting reactants. And so that relies on using stoichiometric conversion. So this is really the application of stoichiometry. Again, a lot of times when you look at stoichiometry, a good example of places that you've encountered it is in kitchen cooking. That's a lot of chemistry-based type conversions, essentially. And so I'm going to give you an example real quick and walk through this terminology. And so in my example, the scenario is that we know we have that if you build a trike, one trike needs 3 tires. So I'm going to abbreviate tires as T, and I'm going to make these conversion factors is to 1 trike. The other thing I know that if I want to build a tricycle is 1 seat is needed for 1 trike. So if I gave you 7 tires and 8 seats, how many trikes are we going to be able to build? And so you could probably easily tell me that you can get 2 trikes and that's it. And what you're essentially doing there in your head is you know that for 7 tires to build 1 trike again is to those 3 tires. And so you can get 2.33 trikes from that, which you can't have a third of a trike. I guess you could have a unicycle, but we're not making unicycles. So then we have 8 seats, and we know that 1 tricycle needs 1 seat, so you could make 8 tricycles. So this is just, again, kind of showing you what we're doing, because again, we're still working with moles and things a little bit less familiar. And so a limiting reactant is the substance. Again, it's a reactant, so it's a starting material to the left of the arrow that limits the amount of other reactants that can combine to make products. And so in this scenario, the limiting reactant, the limiting building material is the tires. You can only make 2 trikes fully with 3 sets of tires and 1 seat. And so this, if this was a chemical reaction, would be a limiting reactant. And so this is holding back that, yes, we have enough for 8 trikes with the seat side of things, but again, those tires are holding us back. So the material that's still left over is going to be the excess reactant. So again, if you think about it, we will have only used up 2 seats because we can only make 2 trikes. So we would have 6 seats sitting around waiting for more tires to show up. This would then be the excess reactant. There is seats left over. And so we're going to look at that with mass to mass conversions. So we worked on how to do those. Now we're applying it. So the first scenario that we have is application, which is really important. You don't want to have a limiting reactant or not enough of a certain reactant if you are launching a rocket. And so it uses hydrazine, which is N2H4, and hydrogen peroxide for a propellant. And so when that reaction takes place, the byproducts, the reactants form nitrogen gas and water. And so what we're going to look at is and identify what is our limiting reactant. So when we start balancing this equation, the nitrogen are balanced. The hydrogen are not. We have a total of 6 on the reactant side and only 2 on the product side. But if I start there, it's going to make things a little bit tricky because I do have an odd number of oxygen. And so from there, if I start by putting let's say a 2 here, what happens is, yeah, I get 2 oxygen, but I still am not to the point of having enough hydrogen here. So the next scenario is if I want to get 6, I can put a 3 here. Well, if I do that, yeah, that gives me 6 hydrogen. The issue is I now have an odd number of oxygen. So let's try bumping this up to 1 more higher coefficient to a 4. So what that does for me is it now gives me an even number of oxygen to work with. So now I need to get 4 oxygen on the reactant side, which is in the hydrogen peroxide. So a coefficient of 2 will take care of that. So from there, my nitrogen are balanced. My hydrogen, I have 4 and 4, so 8. Well, that's 8 there. And then I have 4 and 4. So now we're balanced with 1, 2, 1, and 4. So just like the scenario before, I gave you how many tires and seats we have. this problem is going to give you your starting amount of both reactants. So the first thing we have is it's asking which is the limiting reactant. So what we're trying to figure out here is what are we going to run out of, the hydrazine or the hydrogen peroxide? And so we have 75 grams of hydrazine, N2H4, and I have 50 grams of the hydrogen peroxide. So what we need to do based on their molar masses and the stoichiometric conversions based on the balance equation, we have to decide which of these we're going to run out of first. So the next thing is, in our last topic, we did mass-to-mass conversions, which that's where we're at here. But I told you specifically, you have X number of grams of this reactant, and what is that equal to in X number of grams of a second, or whatever you are solving for, your unknown. And so here, they don't tell you which one to solve for. What you always do is you pick a product. You have two products in this reaction, so you have two different ways to solve this, and you're going to end up at the same exact conclusion. So you're either going to convert these to grams of nitrogen, because nitrogen is a product, or you can solve for grams of water. Again, you'll get different numbers for your final answers depending which of the two products you choose. But however, you again will come to the same conclusion in terms of which one will we run out. So when I set this up, I worked with water. So we are going to convert these both to grams of water to again look at how much product each of these can make, so that we can make some conclusions. So from here, we have 75 grams of hydrazine. So the very first thing that you do is we need to get this converted to moles. That's molar mass. So I have 1 mole of N2H4. By now, we've done a lot of molar mass calculations. You have 2 nitrogens, you have 4 hydrogens. My molar mass I had is 32.02. If you have questions on molar mass, please feel free to reach out to me. So I can see that my grams have canceled, and I'm now at moles of hydrazine. The next step is we are going to make like our currency exchange. Like the trike example, we need our conversion factor. Again, your conversion factor is moles from your balanced equation. So I have moles of hydrazine currently. The stoichiometric part of the problem tells me I have 1 mole of hydrazine is equivalent to 4 moles of water. So I can see moles of hydrazine cancel out. I'm now at moles of water. To make this a better and easier comprehension, we are going to then convert moles to grams. Again, to do that, we need molar mass. We are at water. We need water's molar mass. And we've worked with water a lot again. So water with the 2 hydrogen and 1 oxygen is 18. And again, we're going to multiply by that 18, divide by 1. Again, just to show you how I run this through on my calculator, I take 75 divided by my 32.02, enter that in, I multiply by 4, I times by 18. So I get an answer of 168.64, and I'm just going to round these off to 2 decimal places. And this is grams of H2O. So now we're going to do the same exact thing, except we are going to do this with hydrogen peroxide. So we want to see how much product my hydrogen peroxide can form. So this first part is going to be a little different. I need the molar mass of hydrogen peroxide, not hydrazine. So 1 mole of H2O2, so using their molar masses and adding them up, is 34 grams. Here, I need my mole ratio. My numerator is going to be the same. I'm looking for moles of water. So 4 moles of H2O is to 2 moles of hydrogen peroxide. The last step is going to be the exact same because we're going to the same product to make our comparison. And so again, we're going to take 50, divide that by the 34. What I'm going to do here is times by 4, divide by 2, times by 18. Yeah, you can just multiply by 2 here. Again, I wouldn't worry about simplifying it out. The math takes care of itself. So then we get 211.76 grams of water. Okay, so just like the scenario with the trike, we need to look at and identify which of these is the limiting reactant and which of these is the excess reactant. So what we can say here is that 75 grams of hydrazine will form 168 grams of water. 50 grams of hydrogen peroxide can form 211.76 grams of water. So we have to figure out what we're running out of first. So hopefully that you can see that. And actually, my answer is very different. And I want to double check this real quick. Did I goof something up? 50 divided by 34 times 4 divided by 2 times 18. Yeah, I did goof something up. So let's backtrack real quick, guys. Thought that looked weird. Okay, so 52.94. So now that we have a correct number, and I'm curious what I typed in wrong, but again, that's for a different time. What we have here, so again, 75 grams of hydrazine will make 168.64 grams of water. 50 grams of hydrogen peroxide is going to produce 52 grams of water, essentially. So what we have to interpret is these values relative to here. So what are we going to run out of? Well, whichever is making the lowest amount of product, that's what's going to hold us back, because that's when we're going to start running out of peroxide. So what we're saying here is the hydrazine, so N2H4, and we're going to do this with just this first problem. So again, you have something to refer to as you look at your notes as a source. So N2H4 can produce 168.64 grams of water, but hydrogen peroxide can only produce 52.94. So, because the hydrogen peroxide produces less, that's the key thing here, is that it produces less product, the peroxide is the limiting reactant. So like the scenario with our trike, we ran out of tires long before we ran out of seats. We were only able to make 2 trikes because we only had 7 tires. And so again, that's the same thing that's going on here, is we get this much product and then the hydrogen peroxide's gone and that reaction can't go any further. There's going to be hydrazine left over. So that makes, because that makes the hydrazine our excess reactant. So because N2H4 produces more product, N2H4 is the excess reactant. So again, just like the seats here, we had 2 seats get used up. There were 6 seats left over because of the scenario with the tires. So there's hydrazine left over after this because, again, it will only get utilized into the point of we can make up to 52.94 grams of water, just like we can only make 2 trikes. And then after that, there's still going to be hydrazine left over because of the stoichiometric ratios here. Okay? So there's one more problem, because these do take a little bit longer to work out, with the iron oxide Fe3O4. It's magnetite, and we can make it in the lab by taking iron with steam to make the Fe3O4, and hydrogen's left over. So again, like any stoichiometric problem, the first thing you need to do is balance it. I would start with the iron. We can see with the iron we have 3 on the product side, so we need a coefficient 3 here on the reactant side. Then we need to start taking care of our oxygen and hydrogen. Right now the hydrogen are balanced. I have 4 oxygens on the product side, so 4 here will help me there. That gives me 8 hydrogen, so I need a 4 here to get that to 8. So 3, 4, 1, and 4 are my coefficients. So we have 36 grams of water. So again, that is one of my reactants, and we have to compare it to our other reactant, the 167 grams of Fe. We want to know which of these is limiting and which one is excess. So again, you need to pick a product. You can pick either product. You could solve for Fe3O4. You could solve for hydrogen. Just like our last problem, numerically your answers will be different, but when you interpret them, you will get the exact same answer. So pick either product if there is more than one product. So the first step in each of these is we need to convert both of them to moles. So we have 1 mole of water is 18 grams. The bottom one, 1 mole of iron, is 55.85. So in both of these, we're going to solve for the Fe3O4. So that's going to be my numerator in both scenarios. Is equivalent to, and my denominator, so up top I'm working for water, so that means my denominator is 4 moles of water. And my denominator with my iron is going to be 3. And again, the thing that's nice here is that the Fe3O4 is going to be used the same in both problems. So 231.55 to 1 mole. And 231.55 is to 1 mole. So when you set this up and work it through, we have 36 divided by 18, divide by 4, times that out, 231.55, and we get 115.90 grams of this Fe3O4 is formed. Now let's see how much the iron can make. So we take our 167, divide that by our 55.85, divide that by 3, times that out by 231.55, and we get an answer of 230.5, or let's see, 230.79 it looks like. Okay, so now we need to do the interpretation. If you look, which one is making less product? Based on the stoichiometric ratios with their molar masses, water is definitely making a lot less product than the Fe is. And so that means that we are going to run out of water first because it's making less product. So water is the limiting reactant. And if you look, iron is making more product. That means Fe is the excess reactant. Again, this part right here is going to be the exact same. If you would have solved for hydrogen instead, yes, the numbers would be different. The ratio, though, would be the same. You would still get that water is limiting, iron is excess. If you have questions, please let me know.